Okay, so we talked about the powers and the rules of powers last week, and we really concentrated on dealing with powers of 10 and working with that. And the main reason for that is because our numbering system is really based off of those powers of 10. We've talked briefly about our place values, and I'm assuming you guys all are familiar with them. We started our decimal point and work our way backwards. Of course, it's ones, tens, hundreds. But I can express it like this. It's 10 to the power of 0, which is 1. 10 to the power of 1 is 10. 10 squared is 100. 10 to the third is 1,000. 10,000, 100,000, and so on. In fact, even going the other way with what we saw last week, you can go 10 to the negative 1, which is 1/10. 10 to the negative 2 is 1/100th, and so on like that. And those are all of our place values. It's what's called a base 10 numbering system, where all the place values are exponents with a base of 10. We can get into the algebraic numbering system where the 10 is replaced with x's, and those are our place values. Or we can get into like a binary where the 10s are replaced with 2's, or an octal where we replace them with 8's, and all sorts of things. But anyway, for today, what we want to look at with these being our place values is we want to look at taking a number like 7,200,000 and abbreviating it. A lot of times we would shorten that up and just write it as 7.2 million. Well, another way to abbreviate that, using the place values, instead of writing out the word million, we could use the 10 to the 6th. So we'd write it as 7.2 times 10 to the 6th. And hopefully you guys recognize that as our scientific notation. You may have learned a lot of shortcuts as to how to put a number in scientific notation, but it's these place values that are really the key to it. When we put a number in scientific notation, what we are naming is that first digit and its place value. So the 7 is in the 10 to the 6th of the millions place. So the 7 goes in front of the decimal point, and the 10 to the 6th is our power of 10. It's our place value. So if we have something like 0.0089, well, we use the first non-zero digit is what we use. That's 8, so we're going to make it 8.9. So we put the decimal point after that digit. And we name its place value, 10 to the negative third, so times 10 to the negative 3. So just so you can see where exactly it is those powers of 10 come from. Now I realize most of you have been taught shortcuts for putting numbers into scientific notation. For example, we have 490 million and we want to put it in scientific notation. Most of you are probably taught you put the decimal point after that first non-zero digit, so 4.9, and then the decimal point started here, and it needs to end up down here. So it has to move 1, 2, 3, 4, 5, 6, 7, 8 places. So that becomes 10 to the 8th. You can remember this was a large number, so it has to be a positive power of 10. Or going the other way, like this. Right, that's 9.4 because the 9 is the first non-zero digit. And the decimal point started out here and needs to go here. We went 1, 2, 3, 4, 5, 6. So I write that as times 10 to the negative 6. 6 is because it moves 6 places. The negative is because this was a really small number. It was in the negative place values. At least the negative powered place values. Converting back the other way, of course, is just as easy. Quick review for you. 3.7 times 10 to the negative 8th. We rewrite it, 3.7. The 8 means we have to move the decimal point 8 spots. The negative means it was in the negative place value, so it was a really small number. So we have to move that decimal point 8 spots to make this smaller. So we have to go 1. Now we have to add a 0, 2, add another 0, 3, 4, 5, 6, 7, 8. So the decimal point goes right there. We have 1, 2, 3, 4, 5, 6, 7 zeros, and the 3, 7. I put the extra spaces in there, kind of like using commas after the decimal point to separate out every 3 digits. Not required, but in the medical field, it's starting to become standard practice. Also, in the medical field, it is required now. You put a 0 in front of a decimal point just to make sure it highlights that decimal point. We might have 1.9 times 10 to the 5th. So same thing. We put the 1.9. The 5 tells us we're going to have to move that decimal point 5 spots. It's a positive 5, so that means we're making this a bigger number. So we go 1, have to add a 0, 2, 3, 4, 5. So that is 190,000. I'm going to assume that all of you know how to put numbers into scientific notation. Hopefully at this point you've seen it, if not in math, at least in the chemistry or physics class, and have worked with it. I do want to take some time, however, to go over operations with these numbers in the scientific notation. So let's, for example, take a look at addition. Just a little bit of review. Remember, we talked about when we add or subtract. We take numbers like, well, let's just go 4 inches plus 7 inches. And when we add or subtract, we must have the same name. So we can only combine inches with inches. And when we add or subtract, we combine the counts. 4 plus 7 is 11. And we keep that same name. It stays inches. And we talked about with whole numbers, like 583 plus 214, that the names were hidden in the place values. That's why we had to line up the columns. We could only add 1s to 1s and 10s to 10s and 100s to 100s. Well, when we're talking about scientific notation, nothing has changed. We might have 4.2 times 10 to the 8th. We can only add numbers that have the same names, or like in the whole numbers, that only add digits that add the same place value. When we look at scientific notation, what part of that indicates a potential place value or a name? It's the 10 to the 8th. That is, it's exactly what that is a place value on the number line. So when we add or subtract numbers in scientific notation, we must have that same power of 10. So let's put that in parentheses so we can add it to another number. 4.2 times 10 to the 8th plus 3.7 times 10 to the 8th. So we have the same name, the same power of 10. We go to add. We'll combine the counts. 4.2 plus 3.7 is 7.9. And we keep the same name, times 10 to the 8th. It can get a little bit more complex than that. We can have 5.3 times 10 to the 12th plus 7.5 times 10 to the 12th. This looks pretty simple because we already have the same name, but we combine the counts. 5.3 plus 7.5 is a 12.8 times 10 to the 12th. And there's a slight problem with that. Right now, this is not proper scientific notation because there's currently 2 digits in front of the decimal point. We can only have 1, so we have to move that decimal point over to make this 1.28. Now, obviously, we have to adjust the power of 10. We move the decimal point 1 spot. We have to adjust the power of 10 by 1. The way I remember it is we made this number here smaller. The power of 10 has to get larger. So 12 plus 1 is 13. So 1.28 times 10 to the 13th. We have to be a little careful with that. Let's say we have 7.9 times 10 to the negative 8 plus 4.2 times 10 to the negative 8th. Now again, we have the same power of 10, so it doesn't look like there should be any problems there. We go ahead and combine the count. 7.9 plus 4.2 is 12.1. And we keep the same name, times 10 to the negative 8th. Once again, we have 2 digits in front of the decimal point here, so we're going to have to move that decimal point over 1. This will become 1.21 times. This number became smaller, so the power of 10 has to get larger. Here's where you got to be careful. Negative 8 plus 1 is a negative 7. I'll see a lot of students change that to a negative 9 without thinking. You got to be careful. Negative 7 is 1 bigger than negative 8. So what happens if we don't start off with the same power of 10? Say we have 6.42 times 10 to the 8th plus 9.4 times 10 to the 7th. Well, just like we did with measurements or even fractions, changing them to common denominators, here we're going to have to change the name so that they're the same, which means we're going to have to change one or both powers of 10. Usually what I do when we're adding is I go to the larger power of 10, which is going to be 10 to the 8th. So 6.42 times 10 to the 8th is not going to change. And we're going to change this to be 10 to the 8th. Well, the power of 10 got larger, so the number gets smaller by 1 place value. So that becomes 0.94. And again, we put the 0 in front just to highlight that the decimal point is there. So now we add 6.42 plus 0.94 is 7.36 times 10 to the 8th. Well, let's take a brief look at subtraction. We're subtracting power or numbers in scientific notation. Once again, we must have the same name, same power of 10. So 7.43 times 10 to the 15th minus 2.81 times 10 to the 15th. We have the same name, we have the same power of 10, so we're going to combine the counts. 7.43 minus 2.81 is 4.62, and we keep the same name, 10 to the 15th. Just like with addition, it doesn't always stay quite that simple. Let's say I have 9.14 times 10 to the 11th minus 8.42 times 10 to the 11th. Again, it looks pretty simple because we already have the same names. We do 9.14 minus 8.42 is 0.72. We keep the same name, so times 10 to the 11th. And now, once again, we have a problem. This is not proper scientific notation. Right now, there's a 0 in front of the decimal point. We need to have one non-zero digit in front of the decimal point. So we have to move it back this way to make it 7.2. Now, of course, we move that decimal place one spot, which means we have to adjust the power of 10 by one spot. This number got bigger. The power of 10 has to get smaller. So 11 minus 1 would be 10. So 7.2 times 10 to the 10th. We might have 4.37 times 10 to the negative 8 minus 3.92 times 10 to the negative 8. Again, we have the same power of 10. Doesn't look like it's going to be much of a problem. 4.37 minus 3.92 is 0.45. And we keep the same name, 10 to the negative 8th. So once again, we have to move that decimal point over 1 to make it 4.5. The number got bigger, the power gets smaller. Here's where you have to be careful. A lot of people would throw in negative 7 without thinking, but negative 8 minus 1 is negative 9. So it's 4.5 times 10 to the negative 9th. So what if we have this? 3.71 times 10 to the negative fifth minus 9.82 times 10 to the negative sixth. Now, we said when we're doing addition that we generally change things to the larger place value, the larger power of 10. In this case, that can be a little tricky. Which one is the larger power of 10? Well, if you look really closely and analyze, negative 5 is actually bigger than negative 6. So this is going to stay 3.71 times 10 to the negative 5. This over here is going to become times 10 to the negative 5. The power got larger by 1. The number has to get smaller by 1 place value. So this is 0.982. And now we subtract. So 3.71 minus 0.982 is, I'm going to subtract this one, 2.728, I believe. And times 10 to the negative fifth, and we don't need to adjust that at all. So we're done right there. Let's look at multiplication. As you go to multiply numbers in scientific notation. If you recall, by the way, when we were multiplying before, don't know why my system went nuts there. When we were multiplying before, if we had something like 5 inches times 6 inches, we combined the counts. 5 times 6 is 30. But then we also combined the names. Inches times inches became inches squared. And because of that, because we were also combining the names, we did not have to have the same name to multiply. We could have 4 feet times 8 pounds. And we would combine the counts. 4 times 8 is 32. And also combine the names. Feet times pounds are foot pounds. So when we're dealing with numbers in scientific notation, what that means is we do not have to have the same power of 10. So we can have 3.5 times 10 to the negative 8 times 4.2 times 10 to the 13th. The powers of 10 don't matter. So we'll do 3.5 times 4.2 will give us 14.7. Combining the counts, multiplying this time we're combining with multiplication. Then we also have to multiply or combine the names. 10 to the 8th times 10 to the 13th. Well, from what we talked about on Friday, we add the powers when we multiply exponents. So 8 plus 13 is 21. That is 10 to the 21st. Now we're not quite done yet. There is one more piece we have to do here. We can have 2 digits in front of the decimal point, so we have to move that over. Become 1.47. This number became smaller. The power gets larger by 1. So 10 to the 22nd. So let's have 5.1 times 10 to the 9th times 2.4 times 10 to the negative 6th. So again, we're going to combine the counts. 5.1 times 2.4. 12.24. Times, we're going to combine the powers of 10. 10 to the 9th times 10 to the 6th. Well, or 10 to the negative 6th, I should say. 9 plus negative 6 is 3. So this will become 1.224. We have to move the decimal point over 1. Number got smaller, power gets bigger, so 10 to the 4th. One more example of the multiplication here. So 7.3 times 10 to the negative 12 times 4.8 times 10 to the negative 5. So 7.3 times 4.8, we're combining the counts. 35.04 times 10 to the, we also have to combine the powers of 10. So 10 to the negative 12th times 10 to the negative 5 is 10 to the negative 17. And now, of course, we have to adjust our decimal point again. Got to move that over one to make it 3.504. This got smaller. The power gets larger, so negative 17 plus 1 is a negative 16. So let's look at division. Let's take 1.47 times 10 to the 15th divided by 3.5 times 10 to the 8th. Just like multiplication, we do not need the same name. We're going to go ahead and combine the counts. 1.47 divided by 3.5 is 0.42 times. Now when we're dividing with exponents, we subtract the powers. So 15 minus 8 is 7, so 10 to the 7th. And now again, we have to adjust the decimal point. Now there is nothing in front of the decimal except for a 0. So I have to move it one spot that way to make 4.2. This time, this number got larger, so the power of 10 has to get smaller. 7 minus 1 is 6, so 10 to the 6th. We might have 1.728 times 10 to the 5th divided by 1.2 times 10 to the negative 9th. Same thing. We divide the numbers. 1.728 divided by 1.2 is 1.44 times, divide out the powers of 10, 10 to the 5th divided by 10 to the negative 9th. Well, 5 minus a negative 9, remember that becomes plus a positive 9, so that'll be 14. The decimal point's already in the right spot, so we don't have to adjust anything in that one. So let's try 3.504 times 10 to the negative 4th divided by 4.8 times 10 to the 17th. So we're going to divide 3.504 divided by 4.8 gives us 0.73 times, well, we're subtracting, remember, so 10 to the negative 4th divided by 10 to the 17th is going to be negative 4 minus 17, or negative 4 plus a negative 17, which is a negative 21. And of course, we're not quite done here yet. We have nothing in front of the decimal point except for a 0, so we have to move that over to make this 7.3. This number got larger. The power has to get smaller, so we're going to subtract 1. Negative 21 minus 1 is a negative 22. We can look at powers. 2.4 times 10 to the 7th, if we have to square that. Just like dealing with algebraic numbers, if we had 7x to the 4th and we're going to square it, you would square the number. 7 squared is 49, and then you would do the rules of powers for the variable. When we have the power of another exponent, we multiply the powers. So x to the 4th to the power of 2 becomes x to 4 times 2 is 8. So x to the 8th. Same happens down here. We're going to do the 2.4 squared, which is 5.76. And then the power of 10, well, 10 to the 7th, the second power, 7 times 2 is 14. So 10 to the 14th. We might go to a third power. Let's take 1.2 times 10 to the negative 8th to the third power. Well, it's the same thing. We're going to do 1.2 to the third power is 1.728. So it's 1.728 times Well, 10 to the negative 8 to the third power, negative 8 times 3 is a negative 24. Now in the medical fields, where the scientific notation mainly comes in is dealing with chemistry and medications and stuff like that. There's a little bit more powerful tool. We don't really talk about engineering notation in itself a lot, but its byproduct comes up a lot in the medical science. What engineering notation is, it's very similar to scientific notation, only it limits our power of 10. A power of 10 must be divisible by 3. So you can have 10 to the 0, 10 to the 3rd, 6th, 9th, 12th, 15th, and so on, or negative 3, negative 6, negative 9, and on in that direction. So when we convert a number into engineering notation, like, let's say 380 million, we have to move that decimal point 3 spots at a time. So we'll start out, we can go 1, 2, 3. Well, we can go 3 more. 4. Come on. 4, 5, 6. Well, we can't go 3 more, or there wouldn't be anything in front of the decimal point. In engineering notation, you have to have at least 1 digit and usually no more than 3 digits in front of the decimal point. So this becomes 380 times 10 to the 6th. It can be a little trickier with our decimals. Like here, 5,900 thousandths. We go to move our decimal point, we go 1, 2, 3, and it looks like we can't go 3 more, but if you really look close, you realize you have to. Right now, there'd be nothing in front of the decimal point except for zeros, so we have to go 3 more. So we're going to actually add a 0 back here so we can go 4, 5, 6. So that becomes 590. This would be 10 to the negative 6 because it's in the negative place values. So anyway, why is engineering notation important to us? Why would we go and confuse things by throwing in the engineering notation? Well, because in the real world, we use metric prefixes. I'm going to use electronics, since we haven't gone over the medication dosage yet with the metric prefix. I'm going to use electronics for a second. Just because that's got a lot of good applications anyway. If we have, a volt. Well, if you're looking at that volt as your main unit, you have millivolts. Well, a millivolt is 1/1000th, or 10 to the negative 3 volts. You have a microvolt. A microvolt is 1/millionth, or 10 to the negative 6 volts. And we can go the other way as well. A kilovolt is 1,000, or 10 to the 3 volts. Or a megavolt is 1,000,000, or 10 to the 6 volts. And these metric prefixes fill in. That's all they are, is a power of 10. So if we look at Ohm's law, where we're told that voltage is equal to current times resistance. If I want to find the voltage given a current of 12 milliamps and a resistance of 2.5 mega ohms. This upside down horseshoe looking type thing is the symbol for ohms. Well, looking at it this way, doing that multiplication makes very little sense with those metric prefixes. But I can write it like this. This is 12 milli is 10 to the negative 3. So this is times 10 to the negative 3 amps. Times 2.5 mega is 10 to the 6. So times 10 to the 6 ohms. Now I can do my calculation. 12 times 2.5 is 30. 10 to the negative 3 times 10 to the negative 6 is 10 to the positive 3. And then we have to know a little bit of electronics. An amp times an ohm is a volt. So this is 30, 10 to the third is kilovolts. Or we can have the same thing dealing with power. One of the formulas for power is equal to the current squared times the resistance. So if we have a current of, let's say, 8.2 milliamps squared times a resistance of, let's do 4.5 kilo ohms. The first thing we have to do is, again, we're going to write this out in the engineering notation. This will be 8.2 milli is 10 to the negative 3, so times 10 to the negative 3 amps, that's squared, times 4.5 times 10 to the positive 3 ohms. Now we have to square this. 8.2 squared is 67.24. Ten to the negative 3 squared, well, negative 3 times 2 is negative 6. So that is 10 to the negative 6. This is amps squared right now, not just amps. Now it's got a little 2 there. Times 4.5 times 10 to the third ohms yet. We haven't done anything with that. But now we can go ahead and do that. We have 67.24 times 4.5. 302.58. Now, we might be a little comfortable with those 3 digits in front of the decimal point, but remember, this is engineering notation, so we can have anywhere from 1 to 3 digits in front of the decimal point. Now we have 10 to the 6 times 10 to, or 10 to the negative 6 times 10 to the third. Negative 6 plus 3 is a negative 3. An amp squared times an ohm is a watt. So this is 302.58. 10 to the negative 3 is milliwatts of power. Okay, I'm going to shift gears for a second. The next topic that we would cover deals with dimensional analysis. And I know that if any of you have had physics or chemistry, you've talked about dimensional analysis before. All it is using the dimensions in a measurement to make sure that the calculation works out correctly. For example, let's say that you are given that you're traveling along at 50 miles per hour. I'm going to write that as a fraction, miles per hour, like that. And you want to know how far you would go in 7 hours. Well, if we set this up formally, this is 50 miles over 1 hour times 7 hours go on top like that over 1. And when we multiply here, the dimensional analysis allows us to cross-cancel the hours just like we would a variable or anything else in a fraction. And now we have 50 miles times 7, which is 350 miles. 1 times 1 is 1, so we get 350 miles. The dimensional analysis a part of that was to cancel out the units and realize our answer does come out to be miles. So, and we were looking for a distance, how far we could go in 7 hours. So the fact that the units on our answer do work out to be miles tells us that we most likely calculated correctly. For example, let's say we wanted to know if we were traveling at 40 miles per hour again, and we wanted to know how long it would take us to go 120 miles. Now again, most of you can do that math in your head and get 3. But we can do the whole thing here. Let's say, take our 120 miles. We'll make it a fraction by putting it over 1. We want to convert the miles into time. So what we're going to actually do here is the miles are going to go on bottom and the hours on top. So it's 40 miles per 1 hour. So what I did is I took this 40, remember this means 40 miles over 1 hour, and I flipped it over. I took its reciprocal, and I'm multiplying. In other words, I was dividing by 40, and just took the reciprocal to multiply because I'm dealing with fractions. So now we can cancel out the miles. They cross cancel. 120 times 1 hour is 120 hours. Over 1 times 40 is 40. 120 hours divided by 40 is 3 hours. Now the book takes the dimensional analysis to a little bit of a crazy level. They define things like this: meter to the -1. Well, anything to the power of -1, of course, is just its reciprocal. So m to the -1 or meter to the -1 is 1 over a meter. All we need to know is a unit to the -1 times the main unit is just going to equal 1. Because that's 1 over m times m. Let's make that m over 1, of course. And what you get is m over m, or 1. So the book is going to throw some crazy examples at you like this, where we might have a milligram squared over liter to the -1, meter to the -1, times liter to the -1, meter, milligram. Well, when you work with something like this, it's pretty silly, actually. But we can do this. We can cross cancel the liter to the -1 and the liter to the -1. They cancel out. We also see that we're going to have meter to the -1 times meter. That's going to cancel out. Then we have milligrams squared in milligrams. We can cancel that out with one of those. Of course, milligrams squared is just milligrams times milligrams. Canceling out 1 leaves us with simply the milligram units. Now, I have two major problems with this. First of all, a liter to the power of -1 is really a nonsense unit. And not only that, but there is no such thing as a milligram squared either. But when you're going through some formulas, it does come up that those units get put onto those, or those powers get put onto those units. Like I said, it's a little silly because it's very, very far-fetched to have a formula that does that to you. But the book is going to make that happen for you. It's going to make you go through those exercises. So anyway, for Wednesday, I'm going to have you work on homework on page 87 through 88. 1 through 39, the odd, is going to work on scientific notation. And then on page 103, 1 through 19, the odd, is going to work on the dimensional analysis. On Wednesday, we're going to talk about units and converting measurement units. We'll talk a little bit about where measurement came from and stuff like that, and converting between our standard and metric units, and some special units that are used in the medical field that you might not be familiar with, like grains and minims and stuff like that. So for right now, here's your homework. We'll finish up Unit 2 on Wednesday, and we'll have our test on Friday. Have a great day.